The following video is an unsophisticated essay of physics. It is not peer-reviewed and should not be cited as a truthful source. The goal of this video is to bring forth new speculative ideas that have not been fully explored. In the novella Flatland, a romance of many dimensions, written by Edwin Abbott, a two-dimensional entity in the form of a square exists within its two-dimensional land called Flatland. It sees other geometrical beings as a line in front of him, just as we perceive our vision through 2D images in our three-dimensional world. Between the 16th and the 19th chapter, the square is visited by a sphere which explains to the square how a third axis exists. The sphere also drags the square into this new dimension, called Spaceland, where the square could see his own world from an omnipresent point of view. After this revelation, the perplexed square, who believed only two dimensions existed prior to this estranged meeting, asked the sphere to show him the land with 4 dimensions. Ironically, the sphere was baffled and said to the square that there is no such land, and the very idea of it is utterly inconceivable. Why does this dimensional argument would be linked to special relativity? First, we need to take a look at two imaginary scientists with opposing hypotheses on the behavior of light. The first scientist, who we will call Red, believes that light travels at an absolute speed, which will then have varying velocities for moving observers depending on their direction of velocity. The second scientist, Blue, believes that light travels at a constant speed, and so all observers will see light behaving in a constant manner, whichever their inertial frame of reference. To settle their debate, the two scientists design an experiment that will determine if either hypothesis is false. As both approve their cooperative experiment will yield accurate results, the conclusion must be one of the 3 following outcomes. Red's hypothesis is refuted, Blue's hypothesis is refuted, or the results are accurate but both hypotheses cannot be disproven from the data observed. Red is confident that his hypothesis will succeed as the experiment will take place on Earth, which is always moving around different axes in space. To Red's surprise, once the experiment is concluded, the results point unanimously towards Blue's hypothesis of a constant speed of light for all observers. Red is, however, still not convinced. Together, they tried the same experiment but as distant observers. The experiment is done an additional time but in space at the tremendous speed of 90% the speed of light. Both scientists have top quality equipment to view the results with utmost precision. Red thinks that, from his point of view, light is definitely moving at different velocities around the speedy equipment. It will no doubt confirm Red's hypothesis in this perspective, which will now only prove that the experiment is generally inconclusive. Once again, the experiment from afar has the same results. Red is befuddled as the experiment had no doubt to prove his theory if it was moving at such a high velocity. The perplexed scientist had one last trick up his sleeve. He said to Blue that the experiment must be inconclusive because there was no possible way for the mechanism of the experiment to detect a constant velocity. There must be something broken or a new unexplained behavior of light. Blue simply quoted Einstein and added an insight of his own. All natural science is based upon the hypothesis of the complete causal connection of all events. The reason why the experiment on Earth is the same as the experiment in space is because they have the same causality, the dilation of time and the contraction of space to maintain the constancy of the speed of light will produce the same outcomes in any inertial frame of reference. Red baits his colleague with a second question. Then if we get there in space, right next to our experiment, we would see these effects and conclude that the results have been bent by time dilation and length contraction, and so they would be inconclusive. Blue simply replies, we would still conclude the experiment as valid because we will be equally as bent in time and space as the mechanism itself. Red finally concludes the following. Then if causality must be preserved and if we can explain why, from our perspective, an observer moving at higher velocity will also have the same result as ours, then shouldn't we be able to explain why our experiment on Earth can be biased without us even knowing it? The experiment is therefore biased and cannot deny both hypotheses. The argument Red has used is the same as the square in Flatland. If we can understand how a reference frame could be biased while being oblivious to said bias, then we must conclude that a second reference frame, such as ours, could be under the same spell. If the square is able to see a third dimension, then the sphere should be able to extrapolate and imagine the existence of a fourth dimension. If faster velocities change our perception of time and space, then we should be able to extrapolate and say we may be currently altered without being able to measure this alteration. Let's review these explanations under simple causal connections. I will refer to the stationary experiment as experiment 1 and the experiment done at 90% the speed of light as experiment 2. First, either experiment will always show results to disprove Red's theory under any inertial frame of reference. This is maintained even though experiment 2 could be seen as having different velocities of light from another point of view. The reason why the experiment shows its usual result is the same reason for both frames of reference. There is no additional causal link for either frame of reference. There must be a physical cause that maintains the result for experiment 2, as without it, the result would be clearly different in the point of view of stationary observers. These physical causes are known as length contraction and time dilation. If the experiment 2 is biased in any way, the observers in the same inertial frame of reference must be equally as biased, as they would otherwise signal the warp of the experiment and proclaim the results as distorted. The observers in experiment 1 should be able to see the complete warp of experiment 2. They will also be able to deduce that the observers of this experiment cannot see their own distorted frame of reference. The observers in experiment 1 should be able to extrapolate that their own experiment could be warped. They understand that they cannot see the distortion of their frame of reference. From these explanations, any experiment to uncover the properties of light related to its velocity could be distorted without us being able to detect this distortion. Is there a way to theoretically uncover this distortion by means other than postulating it as a fundamental law? The visible constancy of the speed of light and both time dilation and length contraction are all known physical truths, yet they are stated as fundamental. I will try to explain that basic electromagnetic interactions could explain these physical phenomena. Before getting into mathematics, we must understand the effects of electromagnetism at high velocities. We will maintain the postulations and consequences of special relativity. Let's imagine a human is aggressively T-posing across the solar system at 90% the speed of light. He is holding a lighter in each hand. He tries to light them both at the same time. From his own point of view, nothing special happens. Both light up at the same time in his perspective. To our point of view on Earth, however, simultaneity is not preserved, and the lighter pointing toward his direction of motion will light up a bit later. This maintains the causal link of events. If we could see the light entering the eyes of the human in space, they will indeed arrive at the same time. The fact that simultaneity is not preserved reveals a secondary effect. We can deduce that the neural signal that traveled across his arms to activate the lighters had different velocities. If not, then causality would not be maintained. This can never be the case in such circumstances, as the first postulation of special relativity would not be respected. We must agree that electromagnetism is affected by higher velocities. This effect is not predicted by special relativity, as time would shift differently in opposing directions. If it could, what would happen within atoms themselves, which are maintained by electromagnetism? This is where we revisit the classical theories of atomical structures. Classically, the electrons are maintained in their orbitals as they individually remain in balance in those states. The nucleus projects this stabilizing electromagnetism, and so the position of the orbitals can be considered as the optimal time required for the electromagnetic waves to reach the electrons. More time or length traveled, the less stable the orbital. If we state that the orbital is dependent on the time for electromagnetism to travel from the nucleus to the electrons, then setting an atom to a much higher velocity must change its properties. If we take one lone atom moving at a good fraction of the speed of light, its orbitals facing toward its direction of motion must be closer than those behind it. Even its vertical orbitals will be somehow affected. The increase in time required to travel the usual length, which will be stated as the Bohr radius, is calculated using this formula, which derives from a light cone which emanates from the center of the nucleus and contacts electrons positioned at angle theta from the center of the nucleus. This egg-shaped orbital structure seems unrelated to special relativity. However, if we place this structure within a grid of atoms, which is a state where atoms usually reside, we will see that there is conflict within these boundaries. In classical physics, the position of an electron is the area where the vectorial electromagnetism of all surrounding nuclei and other electrons would sum up to a null vector. In the point of view of one electron, if we sum the pressure of this term from all surrounding nuclei, it will also result in a null vector. When we account for the average time between a nucleus and one of its electrons at angle theta, the equation will change into this. These prior explanations are, to be honest, quite naive. The resulting formula is, however, representative of what we know as time dilation and length contraction. All electromagnetic interactions, which are all the interactions that affect us, are at least slowed down by exactly the Lorentz factor. Then, horizontal interactions are additionally slowed down by the same factor depending on the angle-adjusted Lorentz factor. Again, if the electrons would converge into orbitals to be as stable as possible, the horizontal orbitals would need to contract so that all the electrons would be equally stable around the nucleus. If one of two observers has all his electromagnetic interactions slowed down, then the other would indeed see him as if his actual time is slowed down. His thoughts, heartbeat, and any other interaction is dependent on electromagnetism. Additionally, if the slow observer had all his orbitals tightened in one direction, the other observer would see him as if he was contracted in one dimension. If the strength of electromagnetism is truly altered by velocity, then there will be no doubt that bodies with immense speed will have different properties altered by their own warped electromagnetism. Being warped in such a way also undoubtedly warps your perception of the speed of light to its absolute velocity. As electromagnetic beings, we are always as warped as the electromagnetism that keeps us together, and so we will always see light's speed as constant. Returning on the experiment with red and blue, even if red's hypothesis is true, they will never be able to detect it, as their experiment is always as warped as their movement through space. Our T-posing space traveler can never see the changes his body undergoes, as his perception is biased. Even if he actually activates his lighters at different times, both the light going through his eyes and the neural signals returning to his brain will arrive at relatively the same times as if he activated them in normal circumstances. The equivalent inertial frames of reference and the observed constancy of the speed of light are still preserved. If these explanations were truly the reasons why special relativity is true, then one problem arises. If one observer sees another observer slowed down and contracted due to electromagnetism, then the other should see the normal one sped up and elongated. This is contradictory to the first postulation of special relativity. This is where this whole theory might fall apart if it wasn't already constructed on uncertain grounds. The only thing that could save it would be the preservation of causality. Causality states that the causal connections of events are always the same whichever your point of view. If causality is not preserved, then the physics behind events would be variable. Other than the wave function of particles, the variability of causal links has never been seen. Let's compare relativity versus causality in some thought experiments. First, let's imagine two observers in space. One orbits the other through artificial means such as rockets or anything else. We will call this one orbit and the other planet. Let's say the orbiting observer can accelerate and decelerate as he pleases without causing harm through inertia. Both observers will hold stopwatches set up at the same time to show their proper time. If orbit starts going as fast as he can, which we will postulate as 75% the speed of light, both proper times will inevitably diverge. According to special relativity, planet will see the other's stopwatch getting slower and slower. Causality would also agree with this observation. Planet's stopwatch, according to orbit, should not go faster in any circumstances if we follow special relativity. Causality would simply state the inverse of planet's perception of time, which would mean that orbit sees the other stopwatch as going faster than normal. Now, let's stop orbit's absurd speed. What would be the final state of the stopwatches, and how does special relativity physically explain the differences between the stopwatches without any of them observing an accelerated clock? The second experiment is inspired by minute physics' the rocket and string paradox. The following explanations will critique the facts stated in his video, so be sure to check it out first to be unbiased. Let's imagine two spaceships in space attached with a fragile rope. Initially, they are stationary and distanced by exactly 1 light second. When this timer, that is exactly between both spaceships, hits 9 seconds, the spaceship in the back will accelerate to 1% the speed of light in 11 seconds of his own proper time. When the timer hits 10 seconds, the spaceship in front will accelerate to the same speed, but in 10 seconds. For a stationary observer, both spaceships have come closer than their starting distance, and they should, in the end, have the same velocity. After both reached their desired velocity, they accelerate to 75% the speed of light in 10 minutes of their own proper time. Now, what will happen to the fragile rope? A stationary observer will see the rope tighten as its length is contracted. If the rope breaks at, let's say, 1.1 times its normal length, then it will undoubtedly do so before they reach 75% the speed of light. But what causes the rope to break in the perspective of the spaceships? According to special relativity, they should just see the space between them contract. If the rope breaks, it must be the opposite, which would mean the space between them elongates. Causality would predict exactly this. If a stationary observer sees the two spaceships contract horizontally, yet the space between them remains the same, then conversely to the point of view of the spaceships, the space between them would need to stretch out. What we have here are contradicting events. We have an impossible scenario, which would be that the rope does not break for the spaceships, but it does for stationary observers. This would simply break reality. We also have the special relativity event, where the spaceships inexplicably see the rope break, but this would not maintain its first postulation because the laws of physics would have varied in their frame of reference. Or we have the event which respects causality and states that the space between them has stretched out, inversely proportional to the contraction of the spaceships and the rope. I am well open to criticism of this video. It would go against the basics of science to state ideas as facts. The least this video could do is to strengthen the special theory of relativity. If you understand the true result of the two prior thought experiments, please leave a comment on why either relativity or causality is preserved. Or better yet, explain why both can exist together. There are other physical phenomena which are explained with relativity, such as why we can go faster than light and the force between wires with currents. The second part of this trilogy will try to explore different physical causes of a known phenomena.